Hi guys, I'm Yuki from External Level Japan at Solana Foundation. This is Solana's confidential balances, a way to hide transfer amounts and balances on chain. Now, the moment people hear cryptography or zero-knowledge proofs, they tense up. So today, we'll understand the whole thing with just two parts, a box and a handle, and one crucial thing up front. This is a confidentiality, not anonymity. Only the contents of the box, the amount, are hidden. Who moved which token and when, all stays public. Don't mix those up. Confidential balances is an umbrella for three features. 1. Confidential transfer. This hides transfer amounts and balances. 2. Confidential transfer fee. This hides the fee amount. 3. Confidential mint and burn. This hides how much is minted or burned. All three run on the same foundation. Zero-knowledge proofs and homomorphic encryption, the box and handle of this video. Our main focus is the first one, confidential transfer. First, what's inside an account? A confidential balance isn't one hidden number. It's a set of parts with different visibility. The public balance is a plain number anyone can read. And the pending and available balances are sealed boxes, invisible to the public, though the owner can open them with their key. Then there is the owner quick copy for reading the available balance instantly, and the public key used to make handles. Here is the core idea, the box. When you seal an amount, a fresh random seed is mixed in. So the same 25 produces a completely different looking box every time. Watch reload, and it looks different. Even with a box that holds a different amount mixed in, from the outside you can't tell which boxes hold the same value. Only someone with a handle and their own key can open it. The second part is the handle. You don't make a separate box per recipient. The box stays single. You just add a handle for each person you want to let in. Keys are per person, and each handle is built from that person's public key. Alice's key opens Alice's handle, but it does nothing on both. No handle means no entry, even if you have a key. And because it's one box, everyone who opens it sees the same amount. You can also compute on boxes without opening them. Stack two sealed boxes and you get a new sealed box holding the sum. No key needed to stack. You only need a key to open and read at the very end. So balances update without ever exposing the numbers. That's a homomorphic property. You can add while it stays sealed. Now an obvious question. When you open the box with your key, does the number just pop out? It doesn't. What you get is a counter that guesses up from 0. Small numbers are found instantly, but a huge amount never finishes. The reason, with no cap, the value could grow without bound, so 3 fixes. 1. Cap the amounts. Transfer go up to about 2 to the 48, roughly 281 trillion base units. 2. Split that value into high and low bits and search each small range separately. 3. The owner keeps a sticky note copy and reads it instantly. Why does splitting help so much? Searching a 48-bit number whole needs 2 to the 48 possibilities, a product. Split into low 16 and high 32, the work becomes a sum 2 to the 16 plus 2 to the 32. Turning a multiplication into an addition makes it about 65,000 times lighter. A transfer carries 3 proof tags. The verifier, the chain never opens the box. It reads only the tags and learns this fact is true. The amount itself stays hidden. 1. The equality tag. The sender's balance and subtraction checks out. 2. The validity tag. Each handle is well formed so the recipient can actually open it. 3. The range tag. The contents aren't negative. Together, they block secret information and spending the more than you have while the amount stays sealed. That's a zero knowledge proof. Here is the whole flow. Alice prepares the box, the handles, and the proofs on her own device. What crosses the boundary? This dashed line? Onto the chain is only the box and the proof. The plaintext amount 25 never crosses. The chain verifies the proof. Check, check, check. And the sealed amount moves from Alice's available balance into Bob's pending. Both balances stay boxed. Nothing is revealed. Anything you receive lands in pending first and only becomes available once you apply it. Alice deposits, applies, then sent to Bob. Bob's incoming amount sits in pending. Why isolate it? So that someone else's incoming credit can't rewrite your available balance mid-flight and break a proof you are already building. It's front-running protection. And Bob applies, and now he can spend. What about compliance? The issuer can optionally set an auditor. When they do, every transfers box simply gains one more handle, the auditor's. The public still can't open it, but the auditor can, with their own key, to verify the amount. Confidentiality and oversight together, and all it took was one extra handle. Feature 2. The confidential fee. The fee is encrypted too. Why? The rate is public, so if the fee were visible, anyone could compute amount equals fee divided by rate, and unless the fee hit its cap, recover the amount you try to hide. So the fee goes in a box as well. Dividing reveals nothing. And a proof still certifies the fee really is rate times amount within the cap without showing any number. Feature 3. Confidential mint and burn. How much you mint or burn is a supply change and for an issuer that's sensitive business data. Public amounts would expose inflows, redemption sizes, even client activity. So the amount is sealed. The supply updates, but how much it changed isn't public. Correctness, no faking, is guaranteed by the proofs from earlier, and the issuer and auditor can still see the real numbers. Finally, the box, handle, seed from this video each have real names. A Pedersen commitment, decryption handle, and blinding factor. Same ideas, different words. Thank you. This is the end of this video. Bye.